Howdy everyone, Nir Regev here. Welcome to today's 6-minute paper episode. Today we're reviewing a paper titled Deep Convolutional Encoder for Radar-Based Human Activity Recognition from the lab of Professor Gurbuz from the University of Alabama. The abstract here, the abstract highlights the significance of radar-based human activity recognition in applications such as border control, pedestrian safety, and health monitoring. The authors proposed a 3-layer convolutional autoencoder for this task, showcasing its superiority over other deep learning models like convolutional neural network and conventional classifiers such as SVM. Remarkably, the convolutional autoencoder achieves a 94.2% classification accuracy, which is a significant, actually 17.3% improvement over support vector machines classifier. So this is the introduction. The introduction discusses the interesting radar human gait recognition application, particularly for health applications and for security applications like surveillance. Traditional methods of analyzing radar type time series involve extracting predefined features and using classifiers such as support vector machines. However, as the complexity and similarity of classes increase, these methods' performance degrades. The paper proposes using deep learning, and in particular, convolutional autoencoder to improve classification performance. Here in page 2, we have a total of 11 different people. They collected 1,007 gait samples spanning 12 different classes, and these are the classes: walking, jogging, limping, and walking, left foot dragging, and so on and so forth. The Micro-Doppler signature is, again, as I mentioned in previous episodes, it's analyzed via the short-time Fourier transform, STFT, and they describe how to calculate it here using equation number 1. And then they take the absolute value squared and they grayscale it, normalize it between 0 and 1, and they downsample it to become an image of these dimensions, from this dimension to this dimension. This image will be an input to the classifier. They do also discuss class imbalance, and they use the SMOTE algorithm, the synthetic minority oversampling technique. Is applied on a training data set to prevent imbalance training and to avoid overfitting. In this page, they first of all give examples and of the SMOTE-Generated synthetic spectrogram of a person walking and jogging, and they list the features that they extract in order to use the SVM classifier. These are all spectrograms or micro-Doppler signatures. Okay, and here you can see they compared between SVM, random forest, and XGBoost classifiers. Okay, deep learning architectures. So this section is considering 3 architectures, I guess: the autoencoder, the convolutional neural network, and the convolutional autoencoder. The autoencoder uses unsupervised pre-training to initialize weights, while the convolutional neural network leverages convolution layers to learn localized features of the spectrogram images. The convolutional autoencoder, I guess, combines both approaches using unsupervised pre-training, followed by supervised fine-tuning, and incorporates filter concatenation to improve feature extraction. So the idea is this. They will unsupervised train a convolutional autoencoder. Once the encoder is trained to encode the input image into a latent space, the decoder will be stripped out of the encoder and will be replaced with a classification layer, and then the whole network will be trained or fine-tuned, if you will, from the initial condition that the encoder was in. They also describe how they did a sparsity term, and they introduced it into the cost function, which is here the Kullback-Leibler divergence with a coefficient of beta, which they call the sparsity coefficient. I think that Andrew Ng also called it the sparsity coefficient here in his lecture notes about sparse autoencoders. And you can see the architecture here, full architecture. Sorry about that. You can see the full architecture here, and then you can see the convolution neural network described here with 3 convolution layer, and the convolution autoencoder is described here. Okay, so what are the results? We see that the convolutional autoencoder here is performing best, and with 94% accuracy. After it, the convolutional neural network, and the only autoencoder is performing the worst of the 3, but still a lot better than the classical type classifier like support vector machines. They analyze the computational complexity here, and they showcase some confusion matrices showing the superiority of the CAE, the convolutional autoencoder. So to conclude everything, the paper presents a compelling case for using a convolutional autoencoder for radar-based human activity recognition. The proposed CAE architectures outperforms traditional classifiers as well as other deep learning models like autoencoder and convolutional neural network. And they actually pre-train it and then fine-tune it. That's it for today's episode. This paper demonstrates the power of combining convolutional layers with autoencoders and pre-training it for radar-based human activity recognition. If you found this content valuable, please share it with someone who might benefit from it. Like, subscribe, all the good stuff. And please let me know in the comments what do you want me to concentrate on next, and how can I improve my content to better suit what you guys are looking for and looking to hear. And until next time, stay curious and keep exploring. Regev out.